In this video, we're going to look at limits algebraically, or in other words, what to do when the properties don't directly apply, and you want to find a limit without finding it graphically, because that's just approximating really, or numerically, which is also just approximating, and if your answer is a fraction or something, you might not get the correct answer, either graphically or numerically. So if you want to find exact limits, but the properties don't work, that's what this video is about. So first we're going to try to find the limit as x approaches 3 of 1 over x minus 3 all squared by directly substituting that in. Direct substitution. So by direct substitution, to take this limit, and I am going to write limit as x approaches 3 and what I am taking the limit of here. Make sure you always put what you're taking the limit of. Okay, for this we're going to plug in 3. So it's 1 over 3 minus 3 squared. Well, that's 0. That's 1 over 0. Okay, which is undefined. So for limits of rational functions that produce, upon direct substitution, the form k over 0, where k is a non-zero constant, those will never approach a specific value. Instead, what happens is as the values of x approach this c, or 3 in this example, the numerator approaches k and the denominator is approaching 0. So that means that the numerator is becoming larger and larger. I intended to put more space there. Larger and larger, and the denominator is getting smaller and smaller. Okay, so therefore the fraction itself is getting bigger and bigger. If you have a large number divided by a small number, then your fraction is getting bigger and bigger. So when this happens, we say that the limit technically does not exist. However, usually what this means is that your limit is approaching positive or negative infinity. The value of the fraction it's getting really, really big. Now it could be positive or it could be negative. So the limit, what most people say is the limit is approaching either positive or negative infinity, which you can find out which it's approaching either graphically or numerically, right? It's pretty easy to tell if the function's going up or down. The other type of issue that happens is not when you get a number divided by 0, but sometimes you get what's called an indeterminate form, and 0 over 0 is the most common indeterminate form, although there are others as well. So we're going to try to find this limit. The limit as x approaches 2 of x squared minus x minus 2 all over x minus 2 by direct substitution. So I'm going to plug in 2 and see what happens. In the numerator we'll have 2 squared minus 2 minus 2. And in the denominator we have 2 minus 2. That's 0 over 0. Now 0 over 0, interestingly, it's not just doesn't exist or, infinity. It actually can be anything. The title of this section is indeterminate. That means you're unable to determine the value. So 0 over 0 can actually be anything, which is kind of cool. So limits of rational functions that produce upon direct substitution the indeterminate form 0 over 0, they actually need further work. It means find another way to find this limit. Okay, which is easier said than done, but it usually does work out. So when both the numerator and the denominator of the fraction upon direct substitution produce 0, that's what we're looking at when you get 0 over 0. So this occurs when the numerator and denominator have a common factor that is approaching 0, while x is approaching some other value, some value of c. So That means you basically have a factor that's approaching 0 on top and bottom, but there could be other factors approaching numbers, and that's why we can't tell. So the problem can be eliminated by factoring and dividing out the problem-causing factor. In reality, when you divide out factors, normally it's not okay, but when you're taking limits, it is okay, because when you're taking a limit, you're really only looking at what are the y's doing when x is close to c. So you're not really changing the function at the value at c. So it's okay when you're doing limits to factor and cancel common factors.